Okay, good morning. Hope you had a good weekend. We've got we're in a good place right now. We've no exam this week, right? We've got another week without an exam, but a week from Friday, we have our last exam, which is on the last day of regular instruction, right before finals week. Sorry about that, but it'll get you primed and ready for your final, right? You're going to have to know that material for the final anyway. All right, so we will continue. We're getting into some good stuff here, right? How motors and generators work and things like that, and a lot of applications we see around us that are in the news and important applications. Okay. Today we'll talk a little bit about permanent magnets, but before we do that, is this being shared with you? Why isn't it? Yeah, looks like it. There we go. Okay, before we do that, let's talk about electromagnets a little bit more. And let's take a look at this. So you're gonna rate these from strong, medium, or weak, and repelling or attracting. Strong, medium, weak, attracting, or repelling. We'll just go through and we don't have to rank them. We'll sort of make our own list here. So if you have a coil like this, let's just quickly have a coil of wire. And it's carrying a current like that. What direction is the magnetic field? To the right. Because this looks like this is going to be the same as this. Yeah, they're gonna form loops. They'll wrap around here. I don't have enough room to draw the full. Didn't leave enough room to draw the here. Maybe down here I can draw it. Is that better? Okay, so we're good with this one. And if I wrap it the other way, Let's see, I have to. This one goes the other direction, right? You see that? And how am I getting this? I'm wrapping my thumb. Right, if I have a wire wrapped around this cylinder, I run my thumb in the direction of the current, and then my fingers curl around. And so if the current is coming toward you on the top and away from you at the bottom, I run my thumb that way, and it tells me that everywhere inside the loop, the magnetic field is going that way. That's all I care about, is inside the loop. And if the current was coming away from you at the top and toward you at the bottom, I run my thumb that way, and it would tell me, it's hard for me to turn that way, tell me the magnetic field is pointing the other direction. Okay, we ready to do this one? Let's do A together. What's A look like? The one on the left looks like a magnet with the north pole on which end? The left side or the right side? We're looking at this guy right here. North is on the right side, correct. And the one next to it, I just moved it away so you can't see it. The one next to it, we're looking at this one now. It's the opposite, right? The current's going the other direction. Excellent. So these repel. And what do you think? Strong, medium, weak? Strong, because we have the most coils on that one, right? Where's the least? These 3 is the least, and 5 or whatever that is, 1, 2, 3, yeah, 5 is the most. And here we have 5 and 5. So this is a strong repelling magnets. All right, how about B? Attract or repel? B. So both of these are oriented the same way. So this is attracting, and what do we say, medium? Because one of them is strong and one of them is weak. Is that right? Two Two strong ones I'll say is strong, two weak ones I'll say is weak, and one of each I'll say, call that medium. How does that sound? Where are we? C. That's right. Good. Strong and attracting, because C we would be like, I'm sorry I can't show you this and the other image at the same time. Two magnets that look like this. All right, D. Attract medium. Because these are both like E and F. E would be a weak attraction, and F would be weak repel. Okay. All right. And the idea there is just that we've got, if we had one loop, versus if we had two loops, right? Okay, if you have two loops there, each loop is creating the same magnetic field, so you'd get twice as much magnetic field. That's the idea there. All right. Let's see. Let's do a few of these. We want to find, let's not worry about ranking. Let's just find the magnetic field at point P due to the two wires. And we'll just call that spacing, what should we call it? D. How's that? So find the magnetic field in terms of I and D. They both have the same current. Just call it I. Let's just do case A first. The magnetic field at point B. We're only doing A here right now. Okay, that's the situation, right? Both of them coming out of the page. There we go. There it is. I redrew it. So the magnetic field at point P is the magnetic field due to wire 1 plus the magnetic field due to wire 2. It's a vector addition problem, right? What does the magnetic field due to wire 1 look like if you were standing at point P? Like that, right? What's the magnetic field like at point P from wire 2? That's correct. These are tangent to the magnetic field line. So they both point toward the top of the page. One of them will be bigger than the other one because we're closer to that wire, right? And what do we get? If you remember, the magnetic field from an infinite wire, an infinite straight wire, mu naught I over 2 pi r. And for 1, it's going to be, what is it, 2d? And we're adding to that mu naught I over 2 pi r, which is d for wire 2. And if you don't remember that, or if it's an exam and you have to show that, oops, plug in. There we go. We've got an infinite wire. We pick a path going around that wire, we say the integral around that closed path of B dot ds is mu naught I enclosed. And we know that B is constant as we go around that path, and it's equal, and the path length, so if B is constant, it comes out of the integral. The integral of ds is just s, the length. Well, what's the length of a circle? 2 pi r. And we're only enclosing one current, right? I. So B is mu naught I over 2 pi r. All right, we're good with that one. Let's do a couple of more. We're not going to do all of these. Let's do, okay, we did A. How about B? We're in the middle now between the two wires. One wire, the current's coming toward us. The other wire, it's going away from us. I'll draw it down here. I'll give you a minute to think about it. Yes, what's the direction of B1 at point P? What's the direction of P2, B2 at point P? They both point in the same direction because we're on the right side of one of the wires and we're on the left side of the other wire. So by flipping the current, we get the magnetic field pointing in the same direction from both of them. And we'll do one more. And you can do the rest on your own. You're just using your right-hand rule to see what direction the magnetic field is as you go around the wire. You know that wires create currents, right? The wire on the left is creating a current creating a magnetic field that forms a circle around it. What direction? Counterclockwise. So if you're standing on the left side, it points up. If you're standing on the right side, it points down. The other one goes in the opposite direction. What are we doing? C, where B1, B2, okay? You get the idea. You can do the rest on your own. Now let's take a different vantage point. We're gonna rotate the image by 90 degrees and try one or two more. And the whole idea of this worksheet is just to get you being able to twist your view and work basically the same problem, looking at it from a different vantage point. So we're going to find the force on F due to G and H. We're going to do this one. We're not ranking anything. We're just find the force on F due to G and H. You can do other ones later. Okay, 3. There it is. Okay, what do we have to do? We have to find the magnetic field from H excuse me, right? H is creating a magnetic field. F is a current carrying wire sitting in a magnetic field. It's going to feel a force. Let's figure that out. Oh, let's call it D and 2D, or what do we, oops, where am I going? Yeah, let's just call that D again. So this is D, and this is 2D. And what direction? Okay, out of the page. Now we can find the force on F due to that magnetic field. And let's just call this L. Okay, be careful which current and which field and which, so this is going to be I times L times B, because I and B are perpendicular, the sine of 90 degrees is 1. So this is just ILB. Which I? IF. And the B is from H. So we got 6 times L times whatever we had for the other, mu naught over 2 pi. What is that, 3? And what direction? Towards the bottom of the page, yeah. Now you do the same thing for G and F. Okay. We don't have to do both of them. But practice a couple of those just so you get used to taking a different view, right? You've got here, you're looking at the ends of the wires coming at you, and it's kind of nice because the magnetic fields are in the plane of the page. But if we just rotate that 90 degrees, the wires are in the plane of the page and the magnetic fields now are perpendicular to it. So just, get used to kind of looking at things from different angles. That's the main point here. Okay, let's talk about permanent magnets for a little bit. I go kind of light on the permanent magnet section. If you want to get more information on them, read the book. They talk a lot about diamagnetism and different kinds of magnetism. I'm not going to go into. I'm just going to give you the basics. We'll talk about ferromagnetic materials, and that's about it here. How do we magnetize things and demagnetize them, and that's about it. But there's a lot of there are a lot of little intricacies, and if you're interested, read the book on that. Ferromagnetic materials, meaning iron-like. Iron, we talked about it. Every iron atom has a magnetic moment. It is a tiny magnet. And that comes from a combination of things. Electrons all have a magnetic moment. So fundamental particles in physics have different properties, right? Mass, charge, and one of those properties is spin. Is it a little magnet or is it not? An electron acts like a little magnet. It has a property called spin. So it acts like a little magnet. But when electrons pair up, they typically pair up with their magnetic moments in opposite directions, so they cancel out. So not all atoms are magnets. And then there's some motion due to this cloud of electrons around the nucleus. Sometimes there's some net motion there, even though we know that electrons do not go around a nucleus like planets going around the sun, right? That does not happen. It's a cloud of electrons around the nucleus. They're not orbiting. But if you could imagine for a minute that you have this ball of electrons, this cloud of electrons, and there's some net motion to it, then the charges that are moving around, like, I hate to say it, if it was like an orbiting planet around the sun, if a charged object was orbiting the nucleus, it's like a current right around there. And a circular current acts like a magnet. So you can kind of get this idea that if the electron was a little ball of charge spinning like a top, it would have a magnetic moment because it would be like a little current loop. Okay, it's not a little ball of charge spinning like a top, but it's a way we have of, we call it a model, right? Sometimes models are not correct, but they're useful in helping us understand how something might be. All right, so an iron atom acts like a magnet due to some type of electron motion, if you will. That's kind of a stretch, but because of the electrons, the configuration, etc., orbital motion, an iron atom acts like a magnet, has a magnetic moment. Every iron atom has a north pole, south pole. So as iron forms into a chunk, the magnetic moments of their neighbors align. The magnets like to align with each other. And so we got a chunk of iron here. And we get a region where the magnetic moments of the atoms in that region align with each other. But over here, the magnetic moments, for some reason, decided to align in this direction. And then there's a region over here where they aligned this way. And these are called domains. I think I drew too many domains. I should have drawn fewer. They're going to get bigger as I move across the page here because I'm getting tired of drawing them. There we go. Okay, we've got these domains here, and they just form randomly. So within a domain, the atoms are lining, their magnetic moments are lining up like compass needles, lining up with a magnetic field, sort of. They're reinforcing the magnetic fields from their neighbors. But the neighbors over here decided to align in a different way, and the neighbors over here decided to align a different way, and over here a different way. So we've got these different, pick a direction. Just randomly. You get the idea. Okay, so the domains, these are called magnetic domains. And because the domains are randomly oriented, there's no net magnetic moment. Right? This chunk of iron does not act like a magnet. It's made up of lots of little magnets, but because they're all randomly oriented, the big chunk does not act like a magnet. And normally when you pick up a piece of iron like a paper clip, it doesn't pick up other paper clips, right? Paper clips are typically made of iron. They don't magnetically pick up each other, right? They're randomly, domains are randomly oriented. But what happens if we take this? Heat does play a role. Question about heat. Heat does play a role. I think that's more for losing the magnetism than for getting them to align. But it could be that if you heat it up in a strong magnetic field, you can get them to align. And then if you heat it up and there's not a strong magnetic field, they'll go out of alignment, I believe. Okay, let's take this chunk of iron and stick it into a magnetic field. Or hold it near a strong magnet. I'm going to draw fewer domains this time. Okay, so we've got some now we have this external magnetic field. And what happens is the domains try to align, just like compass needles want to align with the magnetic fields. They feel a torque and they want to align. And so now, instead of completely random, they sort of twist and point basically in this direction. You know, probably not perfectly, but they've twisted a little bit. So now this chunk of iron has a magnetic moment, a north pole on one side and a south pole on the other. Yeah, with iron, with ferromagnetic materials, a shock hitting them, dropping them, will often cause the magnetic moments to go out a little bit. They are aligned. You can get them to align, right, by putting it like this. We saw here, we put it into a strong magnetic field. They align. If we take that strong field away, they will stay. Oftentimes, those domains will they might go back a little bit, but they'll sort of stay aligned, and now you have a permanent magnet. You can take a magnet, you can take a piece of iron, put it into a strong magnetic field and make it magnetic, make it into a permanent magnet. But those domains are kind of sensitive. We kind of got them to go into alignment by putting it into a strong field, but you shock it, you drop it, and they'll kind of want to go back to their original alignment. And we've been drawing electromagnets like this. We've been taking our wire, wrapping it around a cylinder, and getting a magnetic field that looks something like this. But in reality, when we make electromagnets, we wrap them around an iron core. Then when we turn on the current in the coil, what do we get? We get this magnetic field that forms here. But what happens in that iron core? The domains align. So you also get extra magnetism due to the iron core. Oops. Yeah. And so you almost always see electromagnets made by wrapping it around an iron core. We talked about, bumping a magnet, hitting it. So one thing that you can do to keep your magnets strong, these are ferromagnetic materials we're talking about, is keep them stuck together. If you keep your magnets stuck together, it helps the magnetic field from one helps keep the domains aligned in the one next to it, right? They want those field lines to close, and they want to stay, those domains want to stay aligned with the field lines. So if you have a horseshoe magnet like this, oftentimes you'll see them with an iron bar across the top. They call that a keeper. Because it helps keep the magnetic field. Then the magnetic field forms like this. You get these field lines. And it helps to keep the magnetic field lines aligned and keep that magnet a magnet. All right, I've got a couple of just quick video. Did I do the... I have a video of... I don't think there's any sound, but of current carrying wire in a magnetic field. A current carrying wire in a magnetic field. When we turn the power supply on, current will flow out the positive terminal to the left, as you see here. It returns on the black wire to the negative terminal of the power supply. It's going to pass through this strong magnet. That's a north pole, and that's a south pole, so the magnetic field points toward the camera. Stop the video and predict what direction the force will be on this current carrying wire in a magnetic field. Okay, up, I'm seeing up. Let's see what happens. It's 3, 2, 1. Did you see it jump? Let's do it one more time. Okay, So the wire, 3, 2, 1. The wire jumps up out of the magnetic field. Let's do it one more time. When the current's turned on. Okay. And then I think I also have one. Let me see. On magnetizing. Okay, so these bar magnets are really lousy magnets. Every time I go to use these to do like the iron filing demonstration where you see the magnetic field lines or something, every quarter I go to get these magnets and they've lost their magnetism. And so what do? I magnetize them. Put the north end in there, and the south end in there, and boom, put a big current through that coil in there, and now they are nice, strong magnets. Okay, I actually, normally when I do it, I put a, stop. I put a keeper bar across the top. So basically what you have here is each one of these holes in this blue box has a coil of wire in it, a solenoid, if you will. And so I'm putting the magnet down inside of a solenoid. When I push that button, a current flows through that wire. A strong magnetic field is generated. On one side, it's generated down. On the other side, it's generated up. And so you get a north pole on one end and a south pole on the other end. Then you flip them around. Flip the two bar magnets around, you do it again. Okay, you saw how weak they were at the beginning, right? You can barely get them to lift up. Okay. So that's magnetizing. And demagnetizing works in a similar fashion. Let's talk about that. Oh, did I go right past our break? Got excited about magnets, I guess. Let's take a 10-minute break. Sorry about that. Stretch your legs, and we'll come back in 10 minutes. Okay, we're back. A question I missed about work done by a magnet. Work done by the magnet, does it decrease the overall magnetism? I guess the way, if we're talking like permanent magnets like this moving, I guess I would think of like some external force moving the magnet, and then the magnetic field doesn't really do work. It just is transferring the force, the external force on the magnet to the other object, the other magnet. I'm not sure. Yeah, that's how I would look at it. In most cases, I think that's the way we look at it. So the magnetic field itself is not necessarily doing the work, but it's sort of transferring the force from something else, and you could think about the work done that way. Okay. So we've talked about magnetizing, right? You take a piece of iron, you put it in a strong field, you remove that field, and the domains kind of remain aligned, and that becomes now a permanent magnet. A piece of iron that where the domains were randomly aligned, had no magnetic moment, now acts like a permanent magnet. But sometimes you want to demagnetize something. Well, first let me draw what we just talked about. So we magnetizing. If we have you got a chunk of iron sitting in a region of space. You've got your magnetic field sensor. You don't measure anything, right? You start off right here. You don't measure any magnetic field. You turn on an external field, an applied field. And what happens is you measure more than the applied field, because not only do you measure the applied field, you measure the field from the iron magnet that's now a magnet, right? The domains have aligned and it acts like a magnet now. So it's not just a line that's up at a 45-degree angle like that. You actually end up here somewhere. You measure more magnetic field because of that iron, that chunk of iron that's sitting there. Now you remove the external field, and what happens? Some of the domains remained aligned, and you measure with no external field present, you measure a magnetic field because you now have a permanent magnet. So I just tried to make a picture out of what we've been talking about in words. This is called hysteresis. When you go through a cycle and you don't end up where you started, the term for that is hysteresis. So demagnetizing works in a similar fashion. When I was a kid, all TVs were CRT, right? They had picture tubes in them. How does a picture tube work? An electron gets fired towards the screen, and as it's going toward the screen is going to have your image on it, right? As it's going toward the screen, it passes through electric fields or magnetic fields, which steer it up and down or left and right, and it hits some point on the screen and causes it to fluoresce, to give off some light. And then it hits the next point on the screen, and then it hits the next point. One electron beam goes along and hits the points in one row, and then the next row, and then the next row, and it goes through the whole screen. And by the time it gets to the bottom, the first part is starting to fade out. It's not glowing anymore, and the electron beam starts again, working its way through. That's how the CRT, the cathode ray tube TVs work, the big TVs where the electron needs a path to move. Well, what happens if your kid plays with a magnet near the front of that TV, near the screen, and magnetizes a section? That electron, instead of hitting the point where it's supposed to hit, will get deflected at the last minute by that magnetic field because the screen is magnetized now, and your picture will be funky in that area, blurry, weird. It won't look right in that area. It'll be all distorted. So you can go to Radio Shack or Fry's or whatever the electronics store was at the time and get a demagnetizing coil and hold it up to your TV and use it on the TV to demagnetize it. But this is how we typically demagnetize things. We just keep magnetizing them in the opposite direction, but a little bit less each time. And that flips the domain. So if I draw the same kind of graph here, total B field applied we're going to start out with the permanent magnet, right? We've got a permanent magnet. We want to demagnetize it. So we put it in a big magnetic field in one direction, and we get all the domains to align in that direction. Then we flip the magnetic field in the other direction, but we don't quite use as strong a magnetic field. So we don't get all the domains to flip over. So now we're up here. Then we flip the magnetic field back, but we use a slightly weaker magnetic field. So not all the domains end up flipping back. So we end up over here. You get the idea. Then we flip the domains back, but we use a slightly weaker magnetic field this time. And then we go this way, and we go this way. And what happens is eventually you end up with half of your domains aligned this way and half aligned this way, and they cancel each other out. You've removed the net magnetism. And this is important not just for old TV sets. This is, I was talking about this once, and one of my students said, oh, I was stationed on a submarine in the Navy, and we used to have to bring the submarine to degaussing stations periodically, because you don't want, eventually what happens is the submarine sits at the bottom of the ocean for a while, and it starts to pick up from the Earth's magnetic field. It starts to pick up a magnetic moment because it's sitting in the Earth's magnetic field, starts to become a magnet. And you don't want your submarine to be a magnet because it's easier to detect that way. So they have these stations, sub-degaussing stations. And what is it? Looks like a big coil of wire. It also probably wraps underneath, right? It would have to. Goes up the sides, across the top, down the other side, and then it has to come across the bottom somewhere, and the submarine comes in. So it's surrounded, it's inside of a solenoid, basically, right? Big coil of wire, and then they just keep flipping the magnetic field in opposite directions and make it weaker and weaker and weaker and demagnetize the submarine. Okay, that's all I want to say about permanent magnets. So we talked about ferromagnetism. There are other types. Rare earth magnets work on a different mechanism, but the book talks a little bit about some of those. Yeah, your computer disk stores information magnetically, so certainly rubbing a magnet over it or doing something to it to flip the information, to change the information, should should destroy data. I think that's what they do when they blank out hard disks and things. They just keep writing different information to it, right? They'll write a whole bunch of information and then they'll erase it, and then they'll write different information, they erase it, and they just keeps flipping things, and then you can't see any history of what's on there. Okay, we're getting to the good stuff. Yeah, it's all good. It's all good. Faraday's law. I think Faraday's law is a fun one. It kind of, like I said, a lot of stuff. Oh, what did I put these in the wrong order? Yes, I did. That's okay. So we talked a little bit about this when we did our lab last week. We have a magnet and a coil of wire. And we'll hook up our ammeter to our coil of wire. And we'll have our magnet moving toward the coil of wire. And while it's moving toward the coil of wire, we get a current flowing and current being registered on our ammeter. And then we stop the magnet. And what happens? No current flows. And then we remove the magnet. And we get current flowing again, right? In this middle case, the magnetic flux through the coil is the greatest at that point in time. That happens to be when the field is zero. So it doesn't depend on how much magnetic flux we have through the coil. What it depends on is how quickly that magnetic flux is changing. How quickly the magnetic flux is changing. So just remember magnetic flux integral B dot dA, right? It's the magnetic field over some area and how it's penetrating that surface area. Okay, so let's do this. Let's walk through this worksheet together. We have two loops of wire, loop 1, loop 2, sitting out here in front of this big loop of wire. They are the same size. They're held near this big solenoid, same distance. Okay, so everything's nice and symmetric. It says, before the switch is closed, is there current through either of the little loops? So this is the switch they're talking about. over here. So basically no current through the big solenoid, no magnetic field being generated. Everything's sitting here. Is there any current? We're right here right now. Is there any current in either of the little loops before the switch is closed? No, there's no batteries there. There's nothing. There's just wire loop sitting there. Nothing's changing. No magnetic field, no changing magnetic field, nothing going on, no current. Now we close that switch. And just after we close the switch, what happens? Do we get current in those little loops? Yes, it's like moving a magnet toward the loop of wire, right? Earlier. There was no, with the magnet way out here, there's no magnetic flux through that coil. And as it moves closer, we get more and more magnetic flux through the coil and current flows. And so that's what happens here. We had no magnetic flux through the coil. Now, all of a sudden, somebody turned on a big magnet. We've got magnetic flux through our coil. Where's my coil? Magnetic flux through the coil. And so that affects the coil and we get current to flow. Yeah, well, we're going to get there, I think. We're going to get there. So now we've left the switch closed for a long time. Is there current in any of those little loops? No. What's that like? That's like this situation, just holding the magnet close, right? We've got a nice, constant, strong magnetic field, but nothing's changing. So the reason we're getting this is that we saw earlier that charges that are just sitting in a magnetic field do not feel a force. But if they're moving in the magnetic field in certain directions, they feel a force. Well, as far as the charge is concerned, it's not really moving, right? It thinks the magnetic field is moving or changing. So you could view it either way. A uniform magnetic field with the charge moving in it, the charge feels a force, or a stationary charge with the changing magnetic field, the charge will feel a force. But it's much easier to think about the changing field in terms of an induced EMF in the loop of wire. So if I have a loop of wire here, charges in this loop of wire, they're free to move. If I have a changing magnetic field, the charges will feel a force and they'll start to move in the loop of wire, creating a current. But another way to think about a current is if we have a current in this loop of wire, we must have a potential difference causing that current to flow. So another way of thinking of it is not in terms of forces, not that a changing magnetic field creates a force on the electrons and the electrons start to move. Another way of thinking of it is that this changing magnetic flux through the loop through the coil here, through the loop, is inducing an EMF in the loop, and that is causing the charges to flow. So that's the way we're going to think about it for a little bit. So after a long time, No current, nothing's changing. Okay, for the time period where there is current induced in the wire loops, find the direction of the current. Well, what direction is the magnetic field that the solenoid is creating? To the right, correct, because we've got current flowing this direction, which means it's going up this side, excuse me, and coming down the front, right? So that's going to create a magnetic field that is pointing this way. Now what we're going to learn is that those little loops, current gets set up in those little loops. And of course, current in a loop of wire creates its own magnetic flux through the wire. So let's say my current gets going in this direction. What is that, clockwise for you? My current gets going in this direction. And so if I put my thumb in that direction, it tells me that the magnetic field created by that current points toward me, right, away from the camera. Well, what we will see is that if the change that caused the current, so let's say this loop of wire is sitting in a region with no magnetic field, like loop 1 and loop 2 there. And then we close the switch, and now there's a big magnetic field coming toward me, away from the camera, through the loop here, toward me, away from the camera. If that caused current to go in this direction, the current would create magnetic field in to the page, or I guess I should say away from the camera toward me, right? Would create its own magnetic flux away from the camera toward me. And we just said that an increasing magnetic flux away from the camera toward me caused current in this direction. So when the current started, it increased the magnetic flux in this direction, which causes more current to flow, which causes more magnetic flux in this direction, which causes more current to flow. Free energy. All we have to do is turn on a magnetic field, get some current to flow, turn off our magnetic field, and it'll just keep generating its own current forever. We know that's not going to be the case, right? You don't get something for nothing. So it must go the opposite direction. It's the only thing that makes sense. When a magnetic flux is turned on away from the camera toward me, the current must go the other way, because it has to create its own magnetic flux that opposes the changing magnetic flux that caused the current to begin with. That's called Lenz's law. And that's how we determine the direction of the current. The magnetic flux due to the current that's just starting here opposes the change that caused the current to flow to begin with. So if we have no flux here, and we turn on flux away from the camera toward me, then the current has to get set up to counteract that, to try to reduce it back to zero. So it would have to go in this direction or counterclockwise for you, right? So let's take a look at what happens with loop 1 and loop 2. They're sitting here with no magnetic flux through them. We close the switch, and there's magnetic flux pointing to the right. So they have to create a current that points its magnetic flux to the left through the middle of the loop, because it's trying to get back to its starting point. It's trying to get back to 0. I'm going to draw my loops like this. So this is due to, this is the B from the solenoid, right? Its magnetic field has to go this way. The current in loop 1 creates a magnetic field that has to point in the other direction, which means it's going to go what direction? This direction. Out of the page at the bottom of the loop, into the page at the top of the loop. And they're both the same. Loop 1 and loop 2, both the same. Okay? Don't worry, we'll do more of this. The magnitude would be the same also. Question, is the magnitude the same also? Yes, because everything's symmetric. It told us up here, it said they're both the same distance away. They're both the same distance from the axis. So everything's symmetric. They're both getting the exact same change in flux. So the magnitude actually would be the same also. If they weren't perfectly symmetric, you know, if one was if one was kind of at the middle and one was near the edge, then they'd be definitely have different flux. But because they're both symmetrically oriented around the loop, then they're going to be the same magnitude. Okay, let's continue here, and hopefully things will start to come full circle and make some sense. I know we're just throwing a lot out at you right now. The ratio of induced currents for the two loops is found to be equal to the inverse of the ratio of the resistances. What does this observation imply about the ratio of the EMF in 1 to the EMF in 2? Let's see, what are they asking here? They're saying that if we take I1 to I2, the ratio of the two currents, well, V is equal to IR, so that means that this is going to be V1 over R1, which means this is V1 over V2 times R2 over R1. And then they're saying that the, what are they saying? Ratio of the equal to the inverse of the ratio of the resistances. Oh, so V1 has to be equal to V2. That's what they're saying. This has to be 1. That was a roundabout way of getting there, but I think what they should have said is what I said earlier. Everything's symmetric. Whatever is happening to loop 1, the same exact thing is happening to loop 2. So they both have to have the same magnitude of the induced voltage. Yes, if so this, they're talking more general case. If the resistance is different in the two different wires, the currents will be different. What will be the same? The induced EMF will be the same in each one. I think that's where they're trying to go here, is that the induced EMF does not depend on the resistance of the wire. It depends on other factors, the area of the wire, the change in flux, things like that. Does not depend on the resistance of the wire. Okay, and so part B says, if loop 2 is replaced by a wooden loop, would there still be an EMF? What did we just say? It doesn't depend on the resistance. Right. So it doesn't depend on the resistance. It depends on the area and the change in flux and things like that. So the what they're trying to lead you into here is that the EMF still exists in that region of space, but because the wooden loop has very high resistance, basically infinite resistance, there'd be no current. Okay. And then it says, suppose that loop 2 were removed completely. Consider a circular path that the wire used to occupy. Is there an EMF along that path? Yes. Is there current flowing along that path? No. So with induced EMF, we're thinking about there's a region of space. We define a region of space. I can use this. We define a region of space, and a changing magnetic flux in that region of space creates an EMF along the path defining the region. But whether current flows or not depends on whether there's a means for current to flow. But the EMF doesn't depend on the material. The EMF depends on the region of space and how we've defined that, the changing magnetic field, things like that. All right, that brings us to Faraday's law. The induced EMF, this is a way to quantify what the EMF is in the loop. It's equal to the negative d flux dt. This is magnetic flux. That's for a single loop. And we can multiply by n to get it for multiple loops, right? Number of turns or loops. And just to recap here, what is flux? Integral b dot dA. Get in the habit of always writing integral b dot dA. And then think about whether the flux, whether the magnetic field is constant over the area. If the magnetic field is constant over the area, what is the flux? It's just B times A, right? Well, B times A times cosine of the angle. But if the magnetic field is normal to the surface and constant over it, the flux is B times A. But if the flux is not constant over the area, you have to integrate. And I always ask my students, can you think of a real world example where the magnetic field is not going to be constant over the area and you have to integrate to find the flux? What's the answer? The answer is on the exam. That's the answer. A real world example where the magnetic field will not be uniform over the area and you have to integrate to find the flux on one of the next two exams, maybe both of them. Okay, let's call it a day. We will pick up with this worksheet next time and talk more about practice using this. So what we do with Faraday's law is real quick. Faraday's law has like a half a page of rules for minus signs and how you define directions and signs. And if you follow all of them, you get the right direction at the end. But most people, I don't even think our book gives you those rules. Most people, what they do, they use Faraday's law to find the magnitude. So I almost always just throw absolute values around this thing to find the magnitude of the EMF. And we use Lenz's law to find the direction of the induced current. And we will practice that quite a bit as we move forward here. Okay, I'll stick around here for a few minutes and I'll see some of you in lab and the rest of you next time.